All right, hi chemistry class. It is day 61 and we're in distance learning, Wednesday of the 4th week, and just a couple more weeks until school is over. What we are going to deal with today, continue with the subject of intermolecular forces and states of matter. The two are related, and talk about how and why certain molecules stick together, and why the different ways that molecules can stick together. So if we just do a quick review, there's 3 types of chemical bonds that actually combine atoms to make tens of millions of different substances. Of those types of bonds, metallic are between 2 metals. I think I said in the earlier video a metal and a nonmetal. That's of course incorrect. It's between 2 metals. Ionic is between a metal and a nonmetal. And then covalent are between 2 nonmetals. Those are high ionization energy, high electronegativity atoms that don't want to give up their electrons, so they share electrons. Of those 3 types of chemical bonds, the third one, covalent, form independent structures called molecules that can actually be separated, but they can also stick together. And when they stick together, molecules stick together, those are called intermolecular forces. Between molecule forces is what that term means. And they will, depending on how well they stick together, will determine whether they are a solid, they're sticking together really tightly, or a liquid, they're sticking together but loosely and they can move around each other, or a gas, they're not sticking together at all. And the 2 external factors that can determine whether they stick together or not are temperature, that is how much heat energy you put into those molecules, and to break them apart, or if you take heat out, you put them back together again. Their intermolecular forces will pull them back together. And the other is pressure. You can squeeze them together, and that will cause them to come together also, just by literally squeezing them together. Okay, so that kind of brings you up to what we're talking about. Now we're going to talk about what these intermolecular forces are. Okay, so the first one we're going to talk about are ion-dipole forces. So table salt, and that cube there represents table salt. It's Na plus ions, sodium cations, and Cl minus chlorine anions, and they're forming an ionic bond, and they're arranged in a lattice structure like bricks in a wall. Now water is a polar molecule, and it has a negative dipole pointing towards the oxygen atom, that is the negative side of the atom, and it has a positive side which is on the hydrogen side of the water molecule. And the reason is that oxygen is more electronegative than hydrogen, so it tends to pull the electrons in the molecule towards it. It doesn't totally take hydrogen's electrons away from it, that would be an ionic bond, but it does tend to pull them towards it. So it means it has a negative end where the electrons are concentrated and a positive end where the electrons have been pulled away, so you just have the 2 protons from the hydrogen atoms. So the negative oxygen side of several water molecules will point toward a positive sodium ion. So the negative side of water goes over to that cubic structure, and they latch around, they kind of surround a sodium, and they pull it away from that structure. So in water, table salt will tend to dissolve into its ions because each ion has more of an attraction to the water molecule than it does to the other sodiums or chlorines or chlorides. So a water molecule will pull away a sodium. The negative end of a water molecule will pull away the sodiums, the positive cations. And the positive end of a water molecule will go over to those chlorines, those big green circles with the negative signs. And the positive side of the water molecule, which is the side where the hydrogens are, that will pull that away. And so if you look at that diagram closely with all the water molecules surrounding the various sodiums and chlorines, you'll notice that the negative side of the water is pointed towards the sodiums, the blue circles with the pluses, and the positive side of the water molecules is pointed toward the chlorines, the green circles with the negative signs. And it usually is about 4 water molecules, 4 or 5, that will actually pull either a sodium or a chlorine away from the salt. So that's called an ion-dipole force. The dipole is the water molecule. It has a dipole, a positive end and a negative end. That's called a dipole. It means 2 poles. And the ion is either the sodium or the chloride. and that's an ion-dipole force. The positive hydrogen side of several water molecules, as I said, points toward the chlorine ions, and this is called an ion-dipole force. So there it is right there. Both of these effects are called ion-dipole forces. Okay, dipole-dipole forces attract polar covalent molecules to each other. So hydrochloric acid, which is HCl, is polar because a highly polar chloride ion atom pulls the hydrogen electron towards it. Below, the positive hydrogen side of an HCl molecule is attracted to the negative chloride side of another HCl molecule. So those funny little script there is called a delta. It's a lowercase Greek letter delta, and that's what you use to denote not that it's an ion, not that it's a total positive or negative charge, but that it's an electrically neutral molecule that has one side that's more positive and one side that's more negative. One side pulls the electrons toward it, in this case chlorine, so it's a delta negative, and the other side has the electrons pulled away from it. That's the hydrogen, so it's a delta positive. And what will happen is the positive end of one of those molecules will be attracted to the negative end of the other. It's not nearly as strong as a covalent bond that's holding each hydrogen to its own chlorine, but it does attract the hydrogen to another chlorine weakly, and that's called a dipole-dipole force. Water is another example of that. Positive end, negative end, the positive end of one water molecule is attracted to the negative end of another. Okay, London dispersion forces. London dispersion forces are temporary changes in the polarity of a molecule due to the random movement of electrons. Dispersion forces are how nonpolar molecules attract each other. So here you have three atoms, and these are hydrogen atoms, but this is usually done with much larger molecules or atoms. And so what can happen is, if you look at the atom number 1 on the left, when its hydrogen is over on the right-hand side of the proton there, well, let me read this. When the electron in the hydrogen atom on the left moves to the right side, it pushes the second atom's electron to the right. If this effect repeats throughout many atoms, it creates a temporary polarity that attracts the atoms to each other. So you see that the electron in number 1 is over on the right. So what it does is it pushes the electron in atom number 2 over to the right, like that, because they repel each other. And it also creates an attraction between the electron in atom number 1 and the proton and the nucleus of atom number 2. Then atom number 2 can repeat that process with atom number 3. Atom number 2's electron will push atom number 3's electron over to the right, and it will also create an attraction between the electron in number 2 and the proton in number 3. And if this repeats for many, many, many atoms in large molecules, then you can have a fairly strong bond. These are considered temporary dipoles because those electrons could have just as easily been over on the other side pushing in the other direction. So they're not permanent dipoles the way a water molecule has a permanent positive end, the hydrogen end, and a permanent negative end, the oxygen end. So these are London dispersion forces. So they answer the question, why do nonpolar molecules that don't have a positive side or a negative side, like water, why do they stick together? And it's because of these London dispersion forces. But it takes a whole lot of atoms with a whole lot of electrons to give these enough strength to actually form bonds. And so London dispersion forces are strongest in large nonpolar molecules, and you'll see an example of that with some hydrocarbons coming up here. Okay, so London dispersion forces are small but can produce strong attraction between large molecules with many electrons. So here's methane. It's CH4. It's a nonpolar molecule. It's electrically neutral, and the charge is balanced throughout. It has a geometry such that the charge is balanced throughout that molecule. So a CH4 molecule has weak LDF, London dispersion forces, because it has only 10 electrons. Methane, that's CH4, it's natural gas, has very weak LDF and is not attracted to other methane molecules. Now, if we get a little bit larger hydrocarbon, this is octane, it's C8H18. It has 66 electrons. So when they get to being pushed in one direction, the way I described on the last slide, that can create a fairly strong negative dipole on one side and positive dipole on the other. Again, it's considered a temporary dipole because those electrons could just as easily move over to the other side. But if they're pushed in one direction, they'll tend to form a kind of a semi-permanent dipole where they do stay on one side. So this, for octane, this is strong enough to make octane a liquid with other octane molecules. So octane is basically gasoline. It's what's gasoline, and you know gasoline at the gas station comes out in liquid form. And then we can get even bigger molecules. And this one is paraffin. It's what's in candle wax. And as you know, candle wax, although it can melt, it is a solid. So there's a paraffin molecule right there. It's just carbons and hydrogens, just like the previous two molecules, but it has a whole lot of electrons. So paraffin is candle wax, C40H82. It has 322 electrons. This many electrons form strong enough attractions to make paraffin a solid at room temperature. So even though London dispersion forces are the weakest type, they can be fairly strong if you have a large enough molecule with enough electrons, so that when those electrons get pushed over to one side, they create a fairly strong temporary dipole, negative on one side, positive on the other. Okay, another fact about London dispersion forces is that shape affects the strength of London dispersion forces. Longer, flatter hydrocarbons, such as N-pentane on the left, form stronger London dispersion forces than round neopentane molecules on the right, because they fit together tighter and with less space between them. So you can see how you could stack the molecules on the left on top of each other pretty neatly, but the ones on the right, they don't really fit together that well, and so they tend to be spaced out a little bit more and don't have quite as strong London dispersion forces. Okay, last but not least is hydrogen bonds. These are the strongest of the intermolecular forces, and they're fairly rare. They only happen in with very specific atoms and molecules. So hydrogen bonds occur when a hydrogen atom is bonded to the three most electronegative second row elements. That would be nitrogen, oxygen, and fluorine. So if you look over on the right side, on the second row of the periodic table, those are the elements you see. Neon is not included because it is a noble gas. It has a full octet, and it doesn't have any electronegativity. It doesn't want to pull in any more electrons. So if you have a hydrogen attached to either a nitrogen, oxygen, or fluorine, then you can create a hydrogen bond. When oxygen pulls the electrons of hydrogen toward it, an exposed hydrogen nucleus, proton, is left exposed. So that's why I'm showing the hydrogens in these water molecules as being plus signs, not H for hydrogen, but plus sign, because it's really, you have kind of an exposed proton sticking out there because the oxygen pulls all the electrons over towards it. So this proton is attracted to the lone pair of another molecule with a nitrogen, oxygen, or fluorine. The hydrogen atom has a fairly strong attraction to the other atom, though it's not nearly as strong as its own covalent bond. So if you were to look at the two plus signs, the two protons in that top water molecule there, they're most strongly bonded to their own oxygen. That's a covalent bond. That's much stronger than any kind of intermolecular force. But they are attracted over to the lone pairs of another water molecule, and that's what creates a hydrogen bond. So it has to be a hydrogen attached to an oxygen and attracted to the lone pair electrons. The lone pair are the two electrons that don't have anything attached to them in the beginning. They have to be attracted to the lone pair of another water molecule. Now here I'm showing you kind of a mix and match of several molecules. You'll notice that the two on the left are water. They're H2O. They have oxygen as their central atom. And again, let me be sure you're clear on this. We haven't talked about it in a while, of lone pairs. When you draw the Lewis dot structure for water, and we've done that some time ago, then what you end up with is two bonding pairs of electrons. That's where the hydrogens are attached, and two electrons that don't have anything bonded to them, and those are called lone pairs. But they can still attract a positive charge towards them, and so that's what's happening here. So the two molecules on the left are water. The one down at the bottom in the center is ammonia. It's got a nitrogen as its central atom and three hydrogens around it, NH3. And the one up above on the upper right is hydrofluoric acid. And so you can see that's a fluorine with one hydrogen attached to it. So for a hydrogen bond to occur, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine and must be attracted to the lone pair of another nitrogen, oxygen, fluorine atom. Here a hydrogen atom on the water molecule, on the water molecule's hydrogen bonds with a lone pair on a nitrogen. So you can mix and match. The hydrogen on a water molecule attached to an oxygen doesn't have to go to the lone pair of another oxygen. It can go to the lone pair of a nitrogen or of a fluorine. So you can mix and match these, but it has to be one of those three elements. So bonds with the lone pair on the nitrogen atom there. Okay, and then over here a hydrogen atom on the nitrogen atom, hydrogen, bonds with the lone pair on a fluorine atom. So you can just kind of inspect those a little bit, look at them, and see what's happening there. So the two molecules on the left, it's the hydrogen attached to an oxygen, which is being attracted to the lone pair of another oxygen. Then the two in the middle is the hydrogen on an oxygen being attracted to the lone pair on a nitrogen. And then if you look at the two on the right, that's the hydrogen on a nitrogen atom being attracted to the lone pair on a fluorine. So hydrogen bonding works because nitrogen, oxygen, and fluorine pull the electrons away from hydrogen so completely that an exposed proton is left sticking out from the molecule. And that exposed proton, that exposed positive charge, which is really the nucleus of the hydrogen atom, can be attracted to the negative charges of lone pairs on other atoms. And that's called a hydrogen bond. Hydrogen bonds of water are stronger than the hydrogen bonds of ammonia or hydrofluoric acid. So even though all three can form hydrogen bonds, the ones on water are stronger. And the reason really makes sense. Look at the pair on the left. These are both water molecules. There is one hydrogen on a water molecule for each lone pair on other water molecules. So that's a perfect match. So notice it's a perfect 2-for-2 match. You have two positive charges on one of the water molecules, and they can match up with two lone pairs on another molecule. Now, you never have it where two molecules line up the way those two are, but what you'll have is you have a perfect one-to-one relationship between protons and electrons. So that makes the strongest type of bond. Ammonia has only one lone pair for every three hydrogens. So look at that. If you look at an ammonia, it has one lone pair and three sides that have hydrogen. So if it's going to bond with other ammonia molecules, you'll notice there's only one lone pair on each ammonia to attract one of the hydrogen. So the other two hydrogens don't have anybody to bond with, okay? So if you go to a dance and there's 3 times as many boys as there are girls and you want to pair up to dance, there's too many boys for the girls, and so a lot of the boys just end up standing around and don't get to dance. So there's no lone pair to bond for those two hydrogen there. And then hydrofluoric acid has only one hydrogen proton for every 3 lone pair. So this is just the opposite situation. If you have 3 times as many girls as boys, and you match them up to dance, then a lot of the girls won't have someone to dance with. So there's a mismatch in terms of the number of positive charges and the number of negative charges that are trying to pair up to form hydrogen bonds. It's only with water molecules that it's a perfect 2-to-2, or you can call that 1-to-1 relationship. So water hydrogen bonds most efficiently. So water hydrogen bonds the most efficiently and has the strongest hydrogen bonds. So here's a quick summary. Generally, the following is the order of strength of different intermolecular forces from weakest to strongest. London dispersion forces are the weakest because they consist of temporary dipoles, and they're really only influence non-polar molecules. All molecules have them, even polar, even hydrogen bonding molecules. They have London dispersion forces, but they're not the most important forces in those particular molecules. They're most important in non-polar molecules because London dispersion forces are the only type of force that non-polar molecules have. Dipole-dipole forces are next because they consist of the positive and negative ends of electrically neutral molecules. That would be water to water. water to water would be a good example. And ion-dipole forces are stronger because they contain a fully charged ion with the end of a molecule of the opposite charge. So that would be water breaking apart a salt crystal. And finally, hydrogen bonds are generally the strongest. Hydrogen bonds are formed by water molecules being stronger. Hydrogen bonds formed by water molecules are being stronger than other hydrogen bonds. Okay, so that concludes this lesson on intermolecular forces. I just asked you a few questions on this. Go ahead and answer those. This is actually going to be your assignment, I decided, for Thursday and Friday. So it's not a particularly long assignment for a 2-day assignment. And so get this done for, I said Thursday and Friday, I meant Wednesday and Thursday. We don't have any class on Friday. And we'll get into gas laws next week along with solutions. But go ahead and finish this. This will be your last assignment for a week. So this counts as 100 points. So be sure to get this one done. Okay, we have meetings on Wednesday and Thursday on Zoom. I hope that you can join those. And it's just to chat and see how you're doing, if everything's okay at home, and to see if there's anything I can do, or if you're having any issues submitting assignments. You really have to start getting things in if you haven't been doing that. So I look forward to hearing from all of you. You get 25 points extra credit for being on that Zoom meeting. So anyway, I hope to hear from you, and have a good weekend if I don't.